Okay, so this is the lesson on how to graph rational functions using 6 steps. The PDF that I posted, this would be pages 3, 4, and 5. The first step is checking for symmetry. So you need to remember back to Magnet Advanced Algebra, and also when we talked about inverse trig at the beginning of this year, we talked about inverses. And so in Magnet Algebra, we did a topic even, odd, or neither, and we had an algebraic test for determining whether a function was even, odd, or neither. Even functions have y-axis symmetry. Odd functions have origin symmetry, and then obviously if it's neither, there's no symmetry. The graph that you have over here is demonstrating y-axis symmetry. If you fold this graph over, it would show symmetry on the y-axis. So the easiest way to determine symmetry is to create a small table of values, because if we substitute in an x value and get out a certain y value and then substitute the exact opposite x value but still get out the same y value, we can determine that there's an even function and that we have y-axis symmetry. So let's start. We're not going to use a rational function because we just want something quick as an example. So I'm just using a quadratic function. So we're going to create a small table of values, and you want to choose two x values, two opposite x values. When you're working with rational functions, your x values cannot be vertical asymptotes. They can't be undefined x values, but we don't have that situation for square functions. So I'm going to use -1 and +1, two opposite x values. If I substitute -1 in here, I get -2. If I substitute +1, I also get -2. So the opposite x value gave me the same exact y value when I substitute into the function. So the opposite x gives me the same y. And that's how I determine that I have y-axis symmetry. And that's what we're trying to get in step 1. So it's an even function, but the type of symmetry is y-axis symmetry. Also, we're eventually going to graph these rational functions, so you're allowed to plot these 2 points that you just determined with this table of values. So it's additional information you can use for your graph as well. So it's an odd function. If we choose two opposite x's, we should get opposite y's as a result. So even y-axis symmetry, the opposite x's gives us the same y, but here we'll get the opposite y with the same with opposite x values. So use an example here. Again, not using a rational function, just to make things easy. So again, I'm going to choose -1 and +1. If I substitute in -1, I'm going to get -1. If I substitute in +1, I'm going to get +1. So these opposite x's give me opposite y's, and so this graph would have origin symmetry. It's really important that if there's any factoring and reducing that you can do, you do not do any kind of reducing before you test for symmetry. You can go ahead and factor if you want, but do not cross out any factors before you do your symmetry testing. It's very important. Okay. Now we get to step 2, which is vertical asymptotes. Now here's where you want to do any simplifying. So if you could factor and then reduce, now's the time to do that, and you will use that reduced function for steps 2 through 6. So we saw from the warm-up that the vertical asymptotes are related to the denominators. So you want to simplify your function if at all possible, but your vertical asymptotes come from the factors of your denominator or setting the denominator equal to 0. So if I factor this denominator, it's the difference of squares, then I'm going to set each factor equal to 0. I get 2 vertical asymptotes, one at x equals -2 and one at x equals 2. Even though this is factorable, you could still set this equal to 0 and solve. You would just take the square root of both sides after you isolated the square term and use plus or minus. For f of x, there's nothing to factor, so you would just set your denominator equal to 0 and get one vertical asymptote at x equals 1. For h of x, there again is nothing to factor. So if we set our denominator equal to 0, it doesn't factor because there's no sum of squares pattern. Isolate the squared term and then take the square root of both sides. So that means plus or minus. The square root of -1 is the imaginary unit. So when we set the denominator equal to 0, we get imaginary. That tells us there is no vertical asymptote for this function. That just says there are no off-limit x values, or no x values that would give us 0 in the denominator. For g of x, we're able to factor the difference of squares in the numerator and the trinomial in the denominator. And by doing that, we can see that we can simplify by reducing by the factor x minus 3. That creates a whole at x equals 3. We're going to use the remaining factors for the function for everything else. Okay, so we wouldn't use the reduced function for symmetry, but once we reduce it and see that there's a whole at x equals 3, we're going to use the function x plus 3 over x plus 7 for anything else, steps 2 through 6. So for our vertical asymptote, we are going to set x plus 7 equal to 0, and we get there's one at x equals -7. We already said that the whole is at x equals 3, but we need to know exactly where to put that whole. It doesn't just automatically go at like the 0.30. So we take that x value, plug it into the remaining function. So put 3 in for both of these x's, which would give us 6 over 10. And 6 over 10 reduces to 3/5. So the whole is exactly at the ordered pair 3, 3/5. Next up is horizontal asymptotes. So if you remember from the warm-up, that was using limits to infinity rules. So our first limit to infinity, rule 1, is when the degree of the numerator is less than the degree of the denominator. And when that's the case, our limit as x approaches infinity is 0. So here we have a horizontal asymptote of y equals 0. If the degree of the numerator is the same as the degree of the denominator, that's a rule number 2. And we look at those two degree making terms and we just reduce them. And that gives us our limit to infinity. It also gives us our horizontal asymptote. So here it's y equals 2. If we have the limit as x goes to infinity and it's a rule 3, well, normally that would mean that our limit to infinity would be either infinity or negative infinity. So that's not exactly going to tell us what a horizontal asymptote is. So if it's a rule 3 where the degree of the numerator is greater than the degree of the denominator, you have to use long division that we talked about previously to get the asymptote, which will either be slant. I like the word slant, but oblique is a synonym. So we're going to use long division. So we're going to take the denominator and divide it into the numerator. We've got some holes in here. Whatever the degree is, we want to make sure we go down in order. So it's 3x to the 4th. I'm going to put plus 0x cubed minus x squared plus 0x plus 0. I'm just going to take it all the way down the constant. And then we also have a hole here because it's x cubed minus x squared. We're missing the x term, so I'm going to put plus 0x plus 1. That'll just help everything line up when you're doing your long division. So remember, for long division, we just look at the first terms. What do we need to multiply by x cubed to get 3x to the 4th? Well, we'll need to multiply by 3x. So then we take that 3x, we distribute it through this whole polynomial. So 3x times 3x cubed is 3x to the 4th. 3x times negative x squared is negative 3x squared. 3x times 0 x is, 3x times 0 is just 0x squared, which is 0. 3x times 1 is positive 3x. always subtract. If you're doing it correctly, those first terms should go away. So I have 0x cubed minus negative 3x squared. So that's a positive 3x squared. Negative 1x squared minus 0 is still just negative x squared. And 0x minus 3x is negative 3x. And then I start the division one more time. That should be a cube. Missed that. Okay. So what would you multiply by x cubed to get 3x cubed? You would multiply positive 3. So start the process of multiplication over again. Distribute this positive 3 to this polynomial. You get 3x cubed minus 3x squared plus 0x plus 3. And you can really stop at this point because there's nothing else to bring down in your polynomial. So anything you get here is just going to be your remainder. And we look up here. We don't worry about the remainder. In this case, there is a slant asymptote. It's the equation y equals 3x plus 3. So for step 3, that's where you're going to have the most work when it's a rule 3 limit to infinity. Now we're up to step 4. So it is possible for a graph to cross a horizontal or slant asymptote. It is not possible for the graph to cross a vertical asymptote. Vertical asymptotes are undefined values of x that cause division by 0. So that's not possible. But a horizontal asymptote or a slant asymptote can be crossed. If you look at the warm-up on questions 3 and 4, we had 2 vertical asymptotes and 1 horizontal asymptote. Let me see if I can find that real quick. And so that's what we had right here. So in example 3, this horizontal asymptote doesn't get crossed by any of those 3 curves. But in example 4, the curve on the left and the right do not cross the horizontal asymptote, but the piece in the middle does. So it is possible to cross a horizontal asymptote. Basically, the horizontal asymptote applies to the outer curves, but not to the middle curve. So you will see times when that is possible. So let's find out how to determine if our function does in fact cross the horizontal or slant asymptote. Basically, you have to figure out what your horizontal or slant asymptote is. So you get your answer to step 3 and then set the function equal to that. So here, this would be a rule 2 limit to infinity. And so our horizontal asymptote would be y equals 3. So we're going to set our function equal to 3 and solve. So we're going to multiply both sides by the denominator. I'm going to distribute 3 to that trinomial. If I subtract 3x squared from both sides, that'll just go away. So then if I move this 3x over, I have negative 6x equals negative 36, so x equals 6. So this function will cross this horizontal asymptote at x equals 6. So at the ordered pair 6, 3, this graph, this curve, will cross this horizontal asymptote. If you get something that doesn't make any sense, so like you got 5 equals 2, that means there is no crossing of the horizontal or slant asymptote. Last 2 steps are x-intercept and y-intercept. Usually for every function, the x-intercept requires a little more work than the y-intercept. So the x-intercept is a point on the x-axis, which means your y value is 0. So anytime you're trying to find the x-intercept, you replace y with 0. But for rational functions, because we have fractions, our next step would be to multiply both sides by the denominator. So if I made this 0 and I multiply by the denominator, 0 times anything is 0. So that's why it ends up always being the numerator equal to 0. So we set your numerator equal to 0 and you solve, and that would be your x-intercept. So x-intercept at 4/3, 0. Over here, when I set my numerator equal to 0, you could either factor and set the factors equal to 0, or you can isolate the squared term and take the square root of both sides. So I have 2 x-intercepts at 2, 0, and negative 2, 0. For the y-intercept, I missed the example up here. If you set this numerator equal to 0, that doesn't make any sense. That means there is no x-intercept. Okay, back to step 6. Last step, find the y-intercept. A y-intercept is a point on the y-axis, which means x has to be 0. So for this example, if you make all your x's zeros, you're left with -4/1. So your y-intercept is 0, -4. So you should be able to kind of just look at that and tell, making all the x's be zeros, so you get 2 over -3. So your y-intercept is the point 0, -2/3. Here, if I make these x's be zeros, I get 2 over 0. So that's undefined. That means there is no y-intercept for that function. All right, we're going to wrap this up by going through the 6 steps with these 2 practice problems. So your assignment for this week, you have 6 functions. You want to go through the 6 steps, show the work for that, and then graph them. We're not going to pretend that you can't use your calculator because, I don't know if you do or don't, so you can always confirm with your calculator. So that's going to be your assignment module for week 1. Okay, so for the first one, let's go through the 6 steps first and we'll get the graph done. So start with symmetry. If you go ahead and graph this, factor it, that'll help you choose appropriate x values for your symmetry. Remember, we can't use anything that would give us 0 in the denominator that is a vertical asymptote. So I can't use -1 and 1 because those are vertical asymptotes. So I'm going to use -2 and 2. Okay, so if I do that and plug -2 in for x in this function, then I'm going to get 2/3. Then I'm going to plug in +2 and I'm going to get also 2/3. So I have y-axis symmetry. And when I go to graph it, that just will help me be more assured that I did the graphing correctly. So step 2 are my vertical asymptotes. I've already factored my denominator. And so if I set each factor equal to 0, I have x equals -1 and x equals 1. So there'll be 2 vertical asymptotes. Step 3, so some of the steps, it's going to be easier to use the factored form, and some steps it'll be easier to use the unfactored form. And for your horizontal or slant asymptote in step 3, since you're using your limit to infinity rules, it's probably better to use the unfactored form because right here I can see the degrees from the numerator and denominator are the same, so it's a rule 2, and my horizontal asymptote is y equals 1 because I would just be looking at x squared over x squared, and that reduces to 1. Step 4 is whether or not that horizontal asymptote gets crossed. So I'm going to set my function. Again, the unfactored form is probably easier, equal to the horizontal asymptote. You're going to multiply both sides by the denominator. And when I subtract out x squared, I get -2 equals -1. Well, that doesn't make any sense. So that just means that this horizontal asymptote does not get crossed. Step 5, x-intercepts. So you're going to set your numerator equal to 0. That's not factorable, so just isolate your squared term, take the square root of both sides, and that gives you plus or minus square root of 2. So I have 2 x-intercepts, negative square root of 2 comma 0 and positive square root of 2 comma 0. And lastly is your y-intercepts. Remember, y-intercepts is just what you get when you replace your x's with zeros. So again, your unfactored form is probably easier there. So if I replace both of these x's with zeros, I just have -2 over -1, which is 2. So let's look at the graph for that now that we have all our information. So let's see. Just standard graph. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we have 2 vertical asymptotes, one at x equals -1 and one at x equals +1, we have a horizontal asymptote at y equals 1. This horizontal asymptote does not get crossed. Remember from the warm-up that the vertical asymptotes, they drive your curves. So I'm going to have a curve around every vertical asymptote. So I should have a curve over here, a curve in the middle, and a curve to the right. All right, so the x-intercepts I have, square root of 2 is about 1.4, so negative 1.4 comma 0 and positive 1.4 comma 0. Y-intercept at 0, 2. And if you want to plot these extra points that you got from your symmetry table, you've got negative 2 comma 2/3 and positive 2 comma 2/3. So the asymptotes help guide your curves, hug your asymptotes, but also go through your points. So I have a curve over here, and I have a curve over here. I only had the 1 point between the two asymptotes, but remember, we're not crossing that horizontal asymptote, so this piece right here is going to look like that. All right, one more example. So for example 2, start with the symmetry. So in this case, I can see that there'll be a vertical asymptote at x equals 2. So I just can't use 2 in my table. So now I can use -1 and +1. If you plug -1 in for all the x's, you get -4. And if you plug +1 for all x's, you get -2. So opposite x's did not give me the same or opposite y's. So there's no symmetry here. And honestly, you're gonna get no symmetry the majority of the time. Step 2, your vertical asymptotes. There was nothing to factor, so it's just the denominator equal to 0. So 1 vertical asymptote at x equals 2. Step 3, horizontal asymptote or slant asymptote. So this is a rule 3 limit to infinity. The degree of the numerator is greater than the degree of the denominator. So that means you have to long divide. There's going to be a slant asymptote. So we're going to do x minus 2 divided into 2x squared minus 5x plus 5. If I have the x into 2x squared, I need to multiply this x by 2x to get 2x squared. So I'm going to put a 2x up here. Then I'm going to multiply 2x times this whole binomial. So 2x times x is 2x squared. 2x times -2 is -4x. Subtract. Remember, these should always subtract out or you're not doing something right. Then -5x minus -4x, that would give you -x. Bring down the next term. So x into -x. I need to multiply this x times -1 to get -x. And then I'm going to distribute that -1 to x minus 2. So -1 times x is -x. -1 times -2 is +2. Subtract, these will go away. 5 minus 2 is 3, but that's the remainder. So I'm just looking up here. This is the equation of the slant asymptote. Right, so for number 4, I need to know if that slant asymptote gets crossed. Let's see, put this right here. So for step 4, you set your function equal to your horizontal or slant asymptote and solve. So I need to multiply both sides by the denominator. So I have 2x squared minus 5x plus 5. So 2x minus 1 times x minus 2, you have to FOIL that. So if you FOIL 2x minus 1 times x minus 2, you get 2x squared minus 5x plus 2. So what happens is 2x squared goes away, -5x goes away, and you're left with 5 equals 2. Clearly, 5 does not equal 2. So this slant asymptote does not get crossed. Step 5, x-intercepts. So remember, we're setting our numerator equal to 0 for x-intercepts. In order to factor this, you would need two numbers that multiply to give you 10 and added to give you -5. Well, there aren't two numbers that do that. If you graph just this parabola in your calculator, you'll see that it does not touch or cross the x-axis. So because this is not factorable, or if you graph it in your calculator because it doesn't touch the x-axis, there are no real zeros here. So that means that there are no x-intercepts. And then step 6 for the y-intercept. We're just going back up here. We're going to place all these x's with zeros. So that's going to leave us with 5 over -2. So we have one y-intercept at -5/2. All right, so now we're ready to graph. So I can get all that information in one shot. Okay. I had some pre-done graphs already, but this is the third time I've had to redo this video because I keep messing up or running out of time or getting interrupted. So I am drawing my own graphs now. Okay, so draw my graph. I'm going to start plotting my information. I had one vertical asymptote at x equals 2. I have a slant asymptote. It's the equation y equals 2x minus 1. So here is the y-intercept. The slope is 2. Up 2 over 1, up 2 over 1, up 2 over 1, down 2, left 1, down 2, left 1. Doesn't have to be perfect, but to be as accurate as possible. Okay, so the curves are defined by vertical asymptotes. So I'm going to have some curve to the left of the vertical asymptote and some curve to the right. And also that slant asymptote is not getting crossed. So let's see what other information I have. I have a y-intercept at 0, -2.5. Okay, so that's going to be the curve down here, not crossing any asymptotes. From the symmetry table, I can plot these 2 points as well. -1, -4, and 1, -2. So all those points are just on the left side of the vertical asymptote. So it looks like that curve, something like that. All right, so I would guess that the other part of the curve is up here, but if you're unsure, you can always add a point to your table. So the vertical asymptote's at 2. So what if I put in x equals 3 into my table, just to get another point on the graph? So if I did that, if I put 3 into the function, I get 3 squared is 9, so 18. 18 minus 15 is 3. 3 plus 5 is 8. And in the denominator, 3 minus 2 is 1. So I can also plot the point 3, 8. 1, 2, 3, 4, 5, 6, 7, 8. And sketch a curve up there. And that's what my graph looks like for number 2. Okay, remember, check in with me during office hours this week if you have any questions and or need some help completing the assignment that's due at the end of the week, which is called To Infinity.